Welcome back. We're going to go revisit the issue of the four fundamental subspaces, now from the point of view of orthogonality. So let me remind you where we were last time. We talked about having a vector space with an inner product, and if you have a subspace, you can take its orthogonal complements, W perp. That's the set of vectors in V which are orthogonal to W, and that's also a subspace. And the usual picture like this, you have W, then the orthogonal complement looks like that. And last time we talked about a couple of basic facts that the dimension of W and the dimension of W perp add up to the dimension of the ambient vector space V. And furthermore, that you can write any vector in V as the sum of a vector in W plus a vector in W perp, and this can be done uniquely. W and W perp, no, excuse me, W and W prime. There's only one way to do this. So here, W is in W, and I'm saying that W prime is in W perp. Okay, so that's just the general setting of a vector space with an inner product and a subspace. And let's do an example. Let's take V to be R3 in the usual dot product, and let's take W to be our favorite subspace, the one where the sum of the coordinates is equal to 0. So the dimension of W, this is a plane. It's perpendicular to the vector 1, 1, 1. And W perp, this is a misprint here, this W bar is meant to say W perp, is the vectors, the span of the vectors the vector 1, 1, 1. That is to say that if you take the vector 1, 1, 1 and dot it with a vector x, y, z, what you get is x plus y plus z. So if that vector is in W, x plus y plus z is equal to 0, and this is W perp. So W is two-dimensional, W perp is one-dimensional. And let's look at this decomposition. I have an arbitrary vector, say 1, 2, 3. I'm claiming I can write it as a vector in W plus a vector in W perp, which is to say vector x, y, z, where the sum of the coordinates is 0, plus another vector, which is some multiple of 1, 1, 1. Well, let's see. How do you do this? Well, the natural thing to do is to look at this equation like this and bring this vector a times 1, 1, 1 to the other side. So if I do that, I get that 1, 2, 3 minus a times 1, 1, 1 is supposed to be a vector where the sum of the coordinates is 0. And that will tell me what a has to be, because this vector excuse me, is written like this. And if the coordinates really do add up to 0, that tells me that 1 minus a plus 2 minus a plus 3 minus a had better be 0. And that certainly tells me a, which is to say, let's see, 6 minus 3a had better be 0, so I've concluded that a is equal to 2. That's the only choice. So I conclude that 1, 2, 3 is equal to something plus 2, 2, 2. And if you just do the subtraction, you'll see that the something is minus 1, 0, 1, and indeed those coordinates do add up to 0. So that's an example of a vector being written uniquely as a vector in W plus a vector in W perp. Okay. Now, I want to jump back a few weeks and go back to the business about the four fundamental subspaces. So you have an n by n matrix, which gives you a mapping from Rn to Rm. Remember, we talked about there are these four basic subspaces associated with A. There's the, I'm thinking of A as being a map from Rn to Rm, and A-transpose is going the other way. And so you have 4 kernels and images, or 2 of each, I should say. So you have the null space of A, and you have the image of A transpose sitting over here. And then over here you have the image of A and the null space of A transpose. And we saw that the dimensions add up. That is to say, the dimension of the null space of A plus the dimension of the image add up to n. And over on this side, the dimensions of these 2 subspaces add up to m. And that looks an awful lot like the thing we were just talking about orthogonal complements, about the dimensions adding up. The general situation where you have a space and its orthogonal complement and the dimensions add. And you can ask if that's what's going on here. And in fact, that's exactly what's going on here. This picture that I've drawn with the null spaces and images is exactly a case of these orthogonal complements. And that sort of further explains this picture. So that's what I'm going to talk about next. Okay, so here's the picture again. You have Rn and Rm. And over here we have the kernel of A, or the null space of A, same thing, in the image of A transpose. And I'm just going to look at one side for the moment. The theorem is the following. It says that the kernel of A is precisely the image of A transpose perp. These 2 subspaces are each other's orthogonal complements. And, well, that's the key fact. And as a consequence, you conclude that their dimensions add up. The dimension of the kernel of A plus the dimension of the image of A transpose is equal to n. Well, we already knew that. I'm just telling you again. And any vector in Rn can be written as a vector in the kernel plus a vector in the image, and uniquely. So these 2 facts 2 and 3 are just immediate consequences of the discussion about orthogonal complements once you have statement 1, which is that these 2 spaces are indeed each other's orthogonal complements. So it's quite a pretty picture. There's sort of a lot of structure here which explains what's going on. And as I said, really the key fact is 1, because 2 and 3 are immediate consequences of 1 from the previous discussion. Okay, so here once again is our picture. And let's see, the kernel of A is these n vectors, v, such that AV is equal to 0. And now here's the key idea. AV is equal to 0. Well, that's if and only if AV, if you take this vector AV and you dot it with any vector in Rm and you get 0. Remember, a vector is 0 if and only if its dot product with every vector is 0. So the kernel of A can be thought of as the following way. It's the set of vectors such that W transpose AV is equal to 0 for all W. Because this thing W transpose AV is just another way of writing this thing AV dot W. So I'm thinking of all my vectors being column vectors, and when you transpose them, they're a row vector. So this is saying an m row vector times your matrix A times an n column vector is supposed to be equal to 0. And now this is a really nice way to write it, because this is symmetric. This is a scalar, And so by an old trick, we can take the transpose of it and get the same thing, which is that V transpose AW is equal to 0 for all W. Now, what does that say? Well, let's see. This vector A transpose W, if you say this for all W in Rm, this A transpose W is running over the whole image of A transpose. And so this equation is saying that V is perpendicular to the image of A transpose. And that's exactly what I was claiming. Right? So this statement here says that V is in the image of in the orthogonal complement of the image of A transpose. Well, here I started with V being in the kernel of A. And so I've concluded that those two things are the same. The kernel of A and the image of A transpose perp are the same. So that's really the proof. It's really explains it. It's a nice trick to make everything symmetric, but it's a little bit abstract, so let's look at a couple of examples. Let's take A to be 1, 1, 1, and this is a map from R3 to R1. So it takes xyz to x plus y plus z. Let's see. What is the kernel of A? Well, it's the vectors x plus xy z such that this is equal to 0. Right? You apply this matrix to this vector and you get 0. That says that x plus y plus z is equal to 0. On the other hand, A transpose is this. And what's the image of A transpose? Well, if you apply 1, 1, 1, the matrix 1, 1, 1, to the 1 by 1 vector A, get your get your dimensions and m's and n's right here. This is the 3 vector AAA. So the image of A transpose are these vectors AAA. And I said the kernel of A is the xyz plus such that x plus y plus z is equal to 0, and the image of A transpose is these vectors. I'll now write it as a row vector. It's the span of the vector 1, 1, 1. And so you see the kernel of A, if you take something in the kernel of A and dot it with something in the image of A transpose, you get 0 precisely. That's if and only if. So this shows that in this example, the kernel of A is the image of A transpose perp. Okay, so what does this say? Let's look at our picture again. You have Rn going to Rm, and you have the image of A and, the image of A transpose and the image of A. And I'm going to draw boxes around these, and I'm drawing the boxes the same size to indicate that the dimensions of these two spaces are the same. They're the rank of A, which is the same as the rank of A transpose. And then we have these complementary subspaces. Over here we have the kernel of A, and over here we have the kernel of A transpose. And I've drawn these different sizes to indicate that they might well be different dimension. And these boxes indicate that these are complementary in that the two spaces add up to Rn and Rm respectively. And what happens if we apply A to something in A over here, we get to the image of A, whereas if we apply A to something in this box, we get 0. And on the other hand, A transpose going back goes like this, whereas A transpose kills this box. And so this gives a nice way to think about these transformations going in both directions. It's really a bijection back and forth between the image of A transpose and the image of A, and then A and the kernel of A and the kernel of A transpose are just going to 0. And any n linear transformation from Rn to Rm has this kind of picture. And over here, we can write V as something in the image of A transpose plus the kernel of A, and we can write any U by symmetry, by the same argument applied to A transpose, as something in the image of A plus something in the kernel of A transpose. That's the fact I said a moment ago, that these boxes are sort of complementary, and they add up to the two spaces. And it's a nice symmetric picture, and it's often convenient to sort of pass back and forth between the two of them. All right, so let's look at another example. Let's take A to be the following matrix. Kind of a simple example. Let's take the 3 by 2 matrix, which has a little identity sitting in it. So what's this? This is a map from R2 to R3. And let's see, what does it do? Well, its rank is equal to 2. So that says that the image of A transpose is all of R2, whereas the image of A is a two-dimensional subspace of R3. By dimension counting, that says that the kernel of A has to be 0, whereas the kernel of A transpose had better be one-dimensional, so that 1 plus 2, as you well know, equals 3. So let's see, A transpose is this fellow. So let's just write all these spaces down. What is the image of A? Well, the image of A is just the first two coordinates or can be anything, and the last coordinate is 0. Whereas the kernel of A transpose, if you think about it for a moment, is the vector 0, 0, z. And indeed, these two spaces add up to all of R3. They're orthogonal to each other, and they're each other's orthogonal complements. So this is sort of the prototypical example. If you chose the right basis, any example kind of looks like this. When the matrix is simple, it's easy to see in coordinates. Okay, so let's conclude with one last example. Let's take A to be the 2 by 2 matrix 1, 2, 3, and 6, which is a map from R2 to R2. Let's see. The rank of this matrix, as everybody knows, is 1. So that says that the kernel of A, the image of A is one-dimensional, and it's the column space, which is the single vector 1, 3. And on the other hand, the image of A transpose, that's the row space, which is the span of the vector 1, 2. So there we have it, two one-dimensional spaces, one on each side. So that says that both of the kernels are also one-dimensional. The kernel of A, well, let's see, if you take this and set it equal to 0, you see that a vector in the kernel is, for example, the vector minus 2, 1. Or maybe I guess I could also take 2 minus 1. So the kernel is the span of the vector 2 minus 1. It's one-dimensional. And so there it is. And similarly, the kernel of A transpose, well, let's see, A transpose is this thing 1, 3, 2, 6. And so let's see, what's a vector in the kernel of that? That's the equation x plus 3y is equal to 0. And let's take the vector 3 minus 1. So this is one-dimensional, and it has the span, it's the span of just the single vector 3 minus 1. And notice these two spaces are orthogonal to each other. And these two spaces are orthogonal to each other. And A and A transpose go back and forth between these two one-dimensional subspaces at the top.